Welcome to AI Paper Slop, where we summarize the latest AI and tech papers so you don't have to.
Exactly.
We are jumping right into the deep end today because the paper on the desk is Wan-Streamer v0.1. It's end-to-end real-time interactive foundation models by the Wan team at Alibaba Group.
It's a big one.
Yeah, massive. So here is your 60-second TLDR. This team has completely ditched the traditional cascaded pipeline. I mean, there are no more separate models for speech recognition, text generation, or video rendering.
None at all.
Right. Instead, Wan-Streamer uses a single unified transformer. It uses interleaved visual, audio, and text tokens, all coordinated by this Block-causal Attention mechanism.
Which is super clever.
It really is. And it achieves native streaming, full-duplex interaction. It's roughly 200 milliseconds of model-side response latency at 25 frames per second.
So the mission for us today is to basically unpack the how, right? Like, how do you engineer strict causality across an entire multimodal stack?
Yeah, that's the big question.
And, how do you design a dual GPU inference pipeline to mask the immense latency of continuous flow matching? Because that is not easy.
No, definitely not.
Yeah.
But to really grasp the magnitude of what the Wan team pulled off here, we should probably look at the baseline first.
Yeah, let's talk about the Frankenstein pipeline.
The Frankenstein pipeline, exactly.
Because if you are an ML engineer building conversational agents right now, you are almost certainly working with one of those. These systems are inherently asymmetric and cascaded.
Right, you're stacking a bunch of completely different models on top of each other.
Exactly. You start with voice activity detection, or VAD, just to figure out when the user has actually stopped speaking.
Which is already prone to clipping, yeah.
Oh, totally. And then that VAD trigger fires up the automatic speech recognition, the ASR module, to transcribe the audio into text. Then that text gets fed into an LLM to generate a text response.
And we're still not done.
Not even close. You have to pipe that LLM output into a text-to-speech engine, and if you're building an embodied agent, that generated audio finally drives a separate video generator or avatar animator.
And if you ever built one of these pipelines, you know exactly what the so what is here.
Mm-hmm.
I mean, you have waiting time at every single module boundary. You were just stacking latencies.
It's a nightmare for real-time interaction.
It is. And even worse, you are accumulating errors at every step of the handoff. Like a slight misinterpretation by your ASR model becomes a total LLM hallucination.
Right, the garbage in, garbage out problem.
Yeah, and then the hallucination gets translated into incredibly weird phonetic phrasing by your TTS model. It just snowballs.
It really does. But beyond the error compounding, I think the biggest issue is that this cascaded approach structurally prevents true full-duplex interaction.
Right, because human interaction isn't sequential.
Exactly. We don't just sit in silence, listen, pause for a full second, think, and then speak. Our conversations are, well, they're overlapping, like right now.
Yeah, we interrupt each other, we nod, we might adjust a sentence midway through because we saw the other person raise an eyebrow or take a sharp breath.
And the cascaded pipeline structurally forbids that natural rhythm. And the reason it forbids it is because it forces text to be the hidden intermediate representation.
Text is just fundamentally a low bandwidth bridge, isn't it?
It's incredibly low bandwidth. When you convert speech to text to pass it to your LLM, you're stripping away all the acoustic and visual nuance.
Right, you lose the sigh, the hesitation.
You lose the subtle facial micro-expressions. The LLM only sees a sterile transcript, right? And your downstream avatar generator only gets a sterile audio file to lip sync to.
It's kind of like comparing a turn-based board game to a real-time strategy game.
Oh, that's a good analogy.
Like in chess, I take my turn, I move my piece, and then I completely stop. You look at the board, you calculate your move, you take your turn, and you stop.
Which is exactly how the cascaded pipeline works.
Right. But human conversation, and what Wan-Streamer is trying to do, is like playing a fast-paced RTS game, like StarCraft or something. Everything is happening everywhere all at once. Simultaneously.
You have to react to micro movements in real time.
Exactly. So this brings up the fundamental architectural question for the Wan team. If text is normally the hidden bridge between these modules, how exactly is Wan-Streamer coupling the audio-visual states before anything is decoded?
Well, they do it by treating the entire interaction as a single ongoing process.
Okay, so no handoffs.
Zero handoffs. Language, audio, and video, both on the input side and the output side, they are all processed as an interleaved causal sequence within one single model.
Wow.
Yeah, incoming speech and video immediately affect outgoing speech and motion. The generated audio and visual states are coupled within the transformer's hitting states before they're ever decoded into pixels or sound waves.
So the semantic reasoning, the turn taking, all of that is just learned jointly.
Jointly within one persistent interaction state.
Yeah.
Yes.
Okay, I need to pause you right there because making a model causal in text is something we've been doing for years.
Sure, standard autoregressive generation.
Right. You do standard next token prediction, you apply a causal mask so the model can't peek at future tokens, and you're done. But achieving strict causality across continuous high bandwidth audio and video streams, that requires a total architecture rewrite, doesn't it?
It absolutely does. You can't just slap a causal mask on a video feed and call it a day.
Right.
It requires an entirely new framework. The researchers actually call it the streaming contract.
Streaming contract. Okay, what does that entail?
For this to work, every single component in the stack must operate causally. Every newly observed unit from the user must be usable immediately, and every generated unit from the agent has to be emitted and committed back into the interaction history without delay.
So no peeking ahead anywhere in the stack.
Nowhere. To support this, they had to design strictly causal audio and video variational autoencoders, or VAEs, for the streaming latent coding.
Because standard VAEs usually cheat a little bit, right? They use bidirectional context.
Exactly. They look slightly ahead in time to compress a chunk of data effectively. But in a real-time streaming environment, looking ahead in time means waiting. And waiting breaks the latency budget.
Right, you can't afford to wait 100 milliseconds to see what the next frame looks like.
You really can't. So Wan-Streamer uses VAEs that only look at the past and the present. From there, they built causal audiovisual encoders and decoders, and they wrapped the whole thing together with a temporally causal transformer.
Man, for the engineers listening, here is where the mechanics get really wild. Because we need to talk about how this model actually generates outputs.
It's a tricky problem.
Very tricky, because it has to treat discrete modalities, like text, and continuous modalities, like audio and video, very differently within the exact same forward pass.
Right. Text uses standard next token prediction with cross-entropy loss. We all know how that works.
Yeah, it's predicting discrete categories from a vocabulary. But the audio and video responses in Wan-Streamer are in continuous latent spaces. You can't just use cross-entropy for a 25 frame per second video signal.
No, the math just doesn't support that kind of high-fidelity continuous generation.
So they use conditional flow matching, right?
They do. Conditional flow matching is the engine of their continuous generation. Let's look at how the math plays out. For the audio and video modalities, imagine you have a clean target latent, and during training, you introduce Gaussian noise to it.
Okay, standard diffusion setup so far.
Right. At a specific flow time, which we'll call tau, you have a noisy latent. The model's job is to estimate the velocity fields for both the noisy audio and the noisy video latents.
And it conditions that on the current streaming context and that specific noise level tau.
Exactly. Essentially, the model is predicting the trajectory needed to push that noisy representation back into a clean, highly detailed audiovisual state.
Okay, I have to push back on the flow matching math here, because diffusion and flow matching are inherently iterative processes.
They are.
If the model is denoising the current audio and video latents step by step, using that noise level tau and the velocity fields, how does it maintain the context of what just happened a fraction of a second ago?
I see what you're getting at.
Like, if you are constantly updating a KV cache in a transformer, aren't you polluting the cache with all these intermediate noisy flow matching states? How do they avoid recalculating the entire history from scratch every single time they denoise a frame?
That is the brilliance of their Block-causal Attention mechanism. And honestly, it's what keeps the compute cost from spiraling completely out of control.
Okay, how does it work?
The velocity predictions for both modalities are conditioned simultaneously on what the paper explicitly calls the clean streaming context.
The clean context.
Yes. This context is strictly separated from the noisy iterative process. It consists of the past user observations that have already arrived, plus the agent's path responses that have already been fully generated and committed to history.
Oh, I see. So because they're using a shared diffusion transformer, this exact same clean context vector conditions both the audio and the video velocity predictions at the exact same time.
Exactly. The model isn't storing its noisy guesswork in the history.
It's using the solidified past to figure out the trajectory for the present.
Precisely. It uses the clean history to guide the denoising of the current frame, and this shared conditioning is what allows speech, motion, appearance, and the scene evolution to be optimized as a tightly coupled, synchronized response.
So that's why the lips moved perfectly in time with the audio.
Right, because they were being generated by the same continuous velocity field based on the same clean context. And crucially, once those latents are fully denoised and finalized, then they are appended directly to the history as clean context for the next unit.
That is incredibly elegant. But wait, doing all this math continuously creates a massive inference bottleneck? I mean, flow matching is notoriously computationally expensive.
It eats VRAM for breakfast. Seriously. If you've tried running these models locally, you know they chew up processing time. If Wan-Streamer is doing continuous flow matching for audio and video simultaneously, how on earth do they hit 25 frames per second?
That is the big question.
How do you cram all that compute into a tiny 160 millisecond streaming unit?
This is the hurdle that keeps most unified models stuck in the research lab. To solve it, the Alibaba team engineered an inference pipeline they call the Thinker Performer.
The Thinker Performer. I love the architecture pattern here.
It's super smart. They essentially take this massive unified model and surgically split the workload across two separate GPUs. The whole goal is to maximize hardware utilization by overlapping the heavy generation tasks with the state updates. Let's break down that Thinker Performer split because it really is a masterclass in pipelining. GPU 0 is the thinker. At any given streaming step, let's call it step K, the thinker consumes the current user audiovisual observations. It runs the causal encoders, updates the KV cache with that new reality, and then it decodes the previous frame's response latents. So step K-1 for immediate emission to the user.
It sounds a bit like a high-end restaurant kitchen.
Yeah, exactly. The thinker is the expediter standing at the front of the house. They are the ones actually talking to the customer and taking the new order. That's encoding the user observation.
Right, and they're also plating the food that's already done and handing it to the waiter, which is decoding the previous frame's latents.
Spot on. And to take that analogy further, GPU 1 is the performer. The performer acts as the line cook in the back of the kitchen.
Exactly. At the communication boundary across the NVLink, the performer receives the newly updated KV cache slice from the thinker.
It just takes the ticket.
It just takes the ticket. The performer doesn't talk to the customer. It doesn't run encoders or decoders. It puts all of its massive compute power into running that heavy flow matching solver to generate the next clean audio-visual latents for step K.
And once those clean latents are cooked, the performer sends them back to the thinker for the next step.
Right. By decoupling the state update from the latent generation, you overlap the operations. As long as the performers want the time to run that flow matching solver, plus the time to communicate the KV cache and latents back and forth, fits inside a 160 millisecond window.
The system achieves real-time throughput.
Exactly. The performer never wastes cycles running lightweight decoders, and the thinker never bogs down running the expensive diffusion solver.
It preserves the semantic reasoning of a single end-to-end model while drastically reducing the perceived latency. It's brilliant.
It is a highly elegant solution, but there is a catch. Hitting that 160 millisecond window assumes the flow matching solver on the performer GPU is already lightning fast.
Which, out of the box, it definitely isn't.
No. You cannot run a high step count diffusion process in that kind of time frame. So how did they shrink the diffusion math itself?
This brings us to their training regimen. Specifically, the third stage, the distillation.
Right. This is where we get into the weeds of how you actually deploy this thing. During training, they start with a much stronger teacher model.
And this teacher uses classifier-free guidance, right?
Yeah.
CFG.
Yes. It requires a high number of flow matching solver steps to get good visual and audio quality. But for those of you listening who work with diffusion models, you know the problem with CFG.
It requires evaluating the model twice per step, once conditioned on the context and once unconditioned.
Exactly. You absolutely cannot afford that double compute tax during a live 160 millisecond streaming window. You would blow past your latency budget instantly.
So they distill that heavy teacher model into a much more efficient student model.
Yes. The student is trained to absorb the effect of the classifier-free guidance directly into its weights.
Meaning the student only needs to do a single forward pass per step.
Exactly. And it requires significantly fewer overall solver steps during inference, all while preserving the high-fidelity quality of the teacher.
Okay, but absorbing CFG only solves the speed problem. It doesn't solve the long horizon problem.
No, it doesn't.
Because if you spend any time working with autoregressive models, you are intimately familiar with exposure bias. They drift over time.
They absolutely drift.
A model gets a little bit off trajectory early on in a generation, and because it is feeding its own slightly flawed outputs back into itself as inputs for the next step, that error compounds.
Right, a weird pixel becomes a weird artifact.
Which becomes a totally glitched out video frame. Eventually, you end up in a massive hallucination loop. So how does Wan-Streamer fix exposure bias for continuous audio and video over, say, a 5-minute conversation?
They solve it with a technique they call rolling distillation. It's a self-forcing strategy combined with distribution matching.
Okay, break that down for us.
So, standard training often relies on teacher forcing, where the model is fed perfect ground truth history at every step. But that creates a massive train test mismatch.
Because in the real world, the model has to rely on its own imperfect generations. There is no ground truth feed.
Exactly. So instead of just training the student on perfect history, Wan-Streamer rolls the student out over consecutive streaming units and trains it on its own generated history.
Ah, so they force the student to live in its own mess during training.
Basically, yeah. It has to learn how to recover from its own slight mistakes and visual artifacts, which totally eliminates that train test mismatch.
That makes a lot of sense.
They align the distribution of the student's autoregressive rollouts to the teacher's trajectory under realistic, messy rollout conditions.
And by doing this distribution matching over time, it prevents that long horizon degradation.
It does. It keeps the avatar's appearance stable, the scene state consistent, and the conversational rhythm natural, even deep into a long, overlapping interaction.
Okay, let's talk numbers. Because latency is a very, very loaded term in AI marketing right now.
Oh, it's the worst.
If you read press releases, a lot of companies throw the word around without defining what boundary they are actually measuring. First token latency, chunk latency, time to first byte.
It can completely obscure how long the user is actually sitting there waiting. The metrics are notoriously opaque across the industry.
Right, reporting first token latency for a text LLM doesn't tell you how long it takes for the TTS engine to generate the audio.
And it certainly doesn't tell you how long the video renderer takes.
Exactly. But the WAN team avoids that ambiguity. They define their benchmark strictly as model-side signal-to-signal response latency.
Meaning the clock starts the exact millisecond. 160 millisecond audio-visual unit from the user arrives at the thinker GPU.
Right.
And the clock stops the exact millisecond. The fully decoded audio and video response is emitted at 25 frames per second.
Yes. And under that strict end-to-end signal-to-signal protocol, Wan-Streamer achieves approximately 200 milliseconds of model-side latency.
Which is incredibly fast.
It is. But they are also honest about the physics of the internet, which I appreciate. They note that in the real world, you have network transit.
Right, you can't escape the speed of light.
If you add a standard 350 millisecond bidirectional network delay for a remote user talking to a cloud server, you are looking at roughly 550 milliseconds of total interaction latency from the user's perspective.
Which, frankly, is still well under the threshold for what humans perceive as a fluid, natural conversation.
Definitely.
Now, if you compare this to other state-of-the-art models out there, the distinction becomes very sharp. Look at Qwen 3 Omni or Qwen 3.5 Omni.
Great models.
Fantastic interactive models. They hit first packet latencies in the 200 to 400 millisecond range, and Mini CPMO 4.5 is hitting around 580 milliseconds for its interaction latency.
But there is a massive caveat for all of those models. They only output speech or text.
That is the core differentiator here. Wan-Streamer is actively generating a fully synchronized visual avatar response. High-fidelity video output within the exact same causal stream hitting 200 milliseconds model side.
It isn't relying on a separate downstream renderer that takes a clean audio feed and puppets a 3D avatar after the fact.
Right. The visual generation is a fundamental part of the core reasoning loop. The model literally thinks in video just as much as it thinks in audio and text.
That completely changes the game for embodied assistance.
It really does. It proves that you don't need the Frankenstein pipeline to achieve high-fidelity multimodal output. You don't need 5 different models glued together with Python scripts.
You just need a ruthlessly optimized streaming architecture, causal VAEs, and a clever way to split the diffusion math from the state updates, like that thinker-performer setup.
It demonstrates that if you respect the physics of real-time communication at the foundational architecture level, the model naturally knows the chaotic, overlapping rhythm of human interaction.
It's fascinating. So to wrap up this analysis, I'm going to leave you with a final thought to mull over. Wan-Streamer proves that forcing strict block-causal latency constraints onto a single transformer can completely solve the cross-modal synchronization problem.
It makes the RTS game of human conversation possible for machines.
Exactly. But if this interleaved single-stream approach becomes the new standard for full-duplex communication, how might this streaming contract fundamentally alter the way we architect the next generation of embodied robotic control systems?
That's a great question.
Right. Because if a single model can navigate the chaotic, overlapping, real-time strategy game of human conversation and generate continuous video responses, well, navigating the physical world and generating continuous motor control outputs might just be the exact same math.
Something for the ML engineers out there to think about.
Absolutely. Thanks for joining us on this dive into Wan-Streamer, and we'll catch you on the next one.